Welcome everyone to another seminar of mathematics and high energy physics at Physics Latam. Today we are happy to have Yalong Cao. He got his PhD at the Chinese University of Hong Kong in 2016. Cao is currently a senior research scientist at RIKEN Interdisciplinary Theoretical and Mathematics Science program in Japan. He is doing research on algebraic geometry, differential geometry, and mathematical physics with a special emphasis on higher dimensional gauge theory. He has been studying Donaldson-Thomas type theory on Calabi-Yau fourfolds, which is a way to count instantons and coherent shifts on Calabi-Yau fourfolds. And today, he will talk about Gopakumar-Vafa type invariants of Calabi-Yau fourfolds. And thank you for accepting our invitation.
Okay, thank you very much for your nice invitation and the introduction. So yeah, please interrupt me any time during the talk. If you have any questions. So my main object today is a Calabi-Yau fourfolds. So let me give a notation X here to be a smooth projective Calabi-Yau fourfolds over complex number field C. So when I say just projective, I mean just it can be embedded into this a projective space as a closed subspace. And when I say Calabi-Yau, it means the canonical bundle is trivial. So associated with such a space, we can talk about the moduli stack of stable map. I just write a notation. So this is the moduli stack of genus G, unpointed stable maps. So from a curve C to our Calabi-Yau fourfold X, satisfying this homological condition that push forward of the fundamental class of C is some fixed homologic class on our Calabi-Yau fourfolds. So this beta here is, sorry, this beta here is this beta a priori fixed, and this G denotes the genus of this curve, and N denotes number of mark points in this curve. So when I say just a moduli stack, you can just pretend this is some space which parameterize all possible maps from this curve to X, and this stable means the automorphism of this data should be a finite group. So in picture, what this moduli space parameterize is have some Riemann surfaces, and with some mark points which are away from singularities. And this apparently there could be some bubbles attached with this curve. And such curves maps to our Calabi-Yau fourfold X. And this we consider all possible such a map up to some equivalence. So anyway, this is a standard notation you particularly see in the theory of or so-called Gopakumar-Vafa theory. In any case, such a moduli space exists as a proper Deligne-Mumford stack. So when I say this is a Deligne-Mumford stack, so basically you can understand as this is locally look like some space quotient by some finite group G. So the key is that we always have some possible finite group as automorphisms. And when I say proper, it's basically this is some compact space in the Euro notion of topology. So one key feature of this moduli stack is it could be very singular. So such space can be very singular, and also possibly with a different kinetic components of various dimensions. So basically, this space could look like the something like you have something here, you have this here. This typically can be the shape of the moduli space you have in mind. So you have several components with different dimensions, and it's could be very singular. So now the thing is that we want to count the number of points in this moduli space. So what do we want? We want to count this space. So what do we mean by count, right? So let's pretend that this is a zero-dimensional set. So because it's already compact, so it can be only finite number of points. So this count will be just a counting of this a finite number of points. But in general, if you want to count something, so typically you need to deal with three issues. The first is about compactness. So the second is about orientability. And the third is about transversality. I will explain this turn by turn. So the compactness is basically saying that the thing we want to count has to be some compact topological space, which is true in this case because of because we apparently we want to just count curve maps to this x, where the domain curve to be smooth curve, but such a map from a smooth curve does not form a compact moduli space. So the thing is that we need to add these bubbles to make this compact. So such compactness is due to the work of Gromov, and similarly in the setting of this harmonic map by Sachs and Uhlenbeck. So after adding this such a nodal curve and consider such a stable maps, you can just obtain some compact space. So the second is about this orientability, but in this case, everything is defined over a complex number, so it's naturally oriented because everything is over C. So the last issue is the somehow difficult issues is to deal with the case, as I said before, this space could be very singular and with different kinetic components of various dimensions. How do you possibly count such things? So transversality is to make the singular space into some a smooth space in some virtual sense. So typically this what people did is they studied this so-called deformation obstruction theory to your modular problem. And in particular, in this case, the deformation space is H0 of this H0 of this pullback of tangent bundle of X. We have this map F. Remember, we have a map from a curve to our Calabi-Yau X. And this is deformation space. And we have some obstruction space, which is H1 of the same bundle. So why I say this, sorry. So to be more precise, I consider this everything is relative to this moduli of curve anyway. This is some technical part, but just you can ignore anyway. So now the thing is that we have tangent space of this moduli. Sorry, we have tangent space of this moduli space. We have some obstruction space which appears in here. This as higher cohomology space, and there's some coordination map. This is some compressed algebraic map, such that the zero locus of this kappa up to some finite group G that gives you the local model, of your moduli, of the moduli MGM X beta. So the singularity of this moduli space, or this bad behavior of moduli space, is because such kappa is not in general position. So kappa is some just behaves in some very very special way, such as their locus is very singular. Okay, so if you draw a picture, so this is the tangent space. And here you have some obstruction space across the tangent space. So this is some trivial bundle over the tangent space. And you construct some coordination map, which is a section of this bundle. And the zero locus, just zero locus cut out some space. Okay, because this section's not necessarily transverse to the zero section. So it ends up giving you just some very singular space. So basically the idea to achieve transversality is you just perturb this section to make the section to be transverse. So you get some smooth space. Then you just get some nice compact smooth manifolds and try to count there. Okay, so now combine all this let's deal with these three issues. Then what this construction ends up giving you is the construction of so-called virtual fundamental class. So this a priori lives in a homology class, but using this cone construction in algebraic geometry, this can live in this child group of this modular stack. If you are not happy with child group, you can just pretend this is a homology class. Okay, so now the point is that this star is a constant. This cycle lives in a constant degrade cycle, and this particular dimension is called the virtual dimension. And in this case, it's basically the dimension of this minus the dimension of this, which you can compute by Riemann-Roch. And in Gopakumar-Vafa theory, this is that's well known. This is dimension of x minus 3 times 1 minus the genus of curve plus the function class of x times the curve class plus n. N is the number of points. So remember, our x is a Calabi-Yau fourfolds. This is our interesting space. That implies that this virtual dimensions, in this case, is a 1 minus g plus this number of points. So you see here, there's a genus dependence on this virtual dimensions on Calabi-Yau case, which is a different behavior compared to the case of more familiar Calabi-Yau case. Okay, so now the point is that the n is the number of mark points, but there's such adding mark points just don't create curves for you. So that means we just to look at whether we have curves in the Calabi-Yau fourfolds, we can just take n to be 0. Then you see that this virtual dimension is 1 minus g, and when g is bigger than equal to 2, this is always negative. Okay, that means on a generic Calabi-Yau fourfolds, you don't expect to see higher genus curve. You only see genus 0 and a genus 1 curve. That means we can only consider the genus 0 and the genus 1 case. Okay, so now we want to use this cycles to cook up some numbers. So this comes to the this definition of Gopakumar-Vafa invariance. So let's consider the genus 0 case first. So just give this notation, GW 0 beta gamma defined to be some integration over this genus 0 curve with 1 mark points. So here the point is that if you put genus to be 0, you see this is always a positive number. That means the cycle is some positive degrees things. That means you need some natural cohomology class to integrate on the cycle. So the natural thing to do is you add 1 mark points, and then you pull back just some cohomology class on X to your moduli space via this so-called evaluation map. So this evaluation map is from this moduli stack of stable maps to our X. So how to define this map? So remember that any point here is a map from this curve C to X, and with 1 mark points. Then associate this data, we can just evaluate this map at this particular point. Then this lives in X. So this defines this evaluation map. And then this what we do is we can pull back some degree 4 cohomology class on X through this evaluation map to the moduli space. Then we can do integration. So the reason we choose this degree 4 cohomology class is because we consider genus 0 and 1 mark points. So here this is 1 minus 0 plus 1. So this complex dimension is 2. So real dimension 4. So that's why we put a 4 cycle here. So now this is some well-defined numbers, which is in general rational numbers, because as I said, this our moduli space has automorphisms. Something like if this is some point over for example a cyclic group, then the count should be just a 1 over this an order of this group. So that's why you can see these rational numbers. Okay, so this is about the genus 0 case. The genus 1 case is the definition is even easier, because if you put genus equal to 1, so this is 0. If you don't put any mark points, you already get a degree 0 cycle. Then what you do is just count the number of points in these cycles, which basically you integrate 1 on this cycle. So now this is also defines your some rational numbers. Okay, so as I said before, so on the compare Calabi-Yau 4 case, you can only consider this genus 0 and 1. There's no higher genus invariants, not. Or in other words, high genus invariants vanish. So because some people in the audience are have this background in physics, so I just give a remark saying that there's some physical interpretation of this such a invariance. You can write it as some infinite dimensional path integral, and this you have some action functional, and you have some observables phi 1 to phi n. You integrate or some measures, and such an integration over all kind of maps. This is all maps from your curve to X. This can be non-holomorphic map or just smooth map or continuous map. And by something called a supersymmetric localization, you can just formally reduce such things, localize such things to integration over this moduli of stable maps I just mentioned before, and also some integration on some cycle here. So this is such a path integral interpretation is was due to written many years ago before this rigorous definition of Gopakumar-Vafa invariance. Okay, so you see that Gopakumar-Vafa invariance is capture this path integral gives you a way to make sense this supersymmetric path integral. Okay, so now the things we are interested in is about this rational numbers. So because the geometric meaning of such a Gopakumar-Vafa invariance is a count. Let me draw a picture. It's a count of this curve. So X is our Calabi-Yau fourfolds. So such a thing is that we want to count some curves. Sorry, maybe there's no higher genus. It's a count of curves through these maps from curve to our X. And in the genus 0 case, we just put some cycles in here, and this curve should meet the cycles. That's the meaning of this intersection numbers. But what you want to do is, anyways, it's counting, but you want to find a integer value counting, because that's the intuitive that's intuition is from our daily life. If you want to count something, we should get integers. So now the question is about this integrality questions, in the sense that the Gopakumar-Vafa invariants are rational numbers, but in general not integers. So the questions are, what are maybe honest, maybe honest with quotation mark, a curve counting invariance. Honest, at least what we mean is at least it should be integers. So now the stories began from this important work of Clem and Pandare. This is in the year of 2007. So what they do is that they propose to define two series of numbers, n0 beta gamma and n1 beta for any curve class beta by the following two formulas. So let's talk about this genius zero formula first. So the left-hand side is the Gopakumar-Vafa invariance we just defined by integration of virtual class. Now the right-hand side is a sum over all possible positive integers which divides a beta. And then we put a coefficient here, 1 over k squared, and we just put n0 beta over k here, which the things we want to define. So here the k divides beta means that beta over k should exist as an integer coefficient homology class. So if you fix a non-zero effective class beta, such possible case is a finite set. So this sum is a finite sum, so it makes sense. And another thing is that this so-called Mobius inversion formula you can search just on the internet. Saying that you can invert this formula basically. That means that you can define this n0 beta by this GW0 beta. So this two series of number, if you vary all possible beta, they contain equivalent informations through these formulas. Okay. So in this way, we define some rational numbers through the just Gopakumar-Vafa invariance defined by some integrations. So there are similar genus 1 formula, which is more complicated. Let me just write it down first. So the left-hand side is a genus series of genus 1 invariants. So we sum over all possible beta curve class, and we put some formal parameter q to power beta to label this curve class beta. And the right-hand side has 3 parts. So the first part is contains this n1 beta we want to define. And here there's some factors involving this function sigma d, which is defined by the sum of all possible k, positive k, which divides this number d. So the second part involves this n0 beta we just defined from the first formula. Here, we put the second Chern class of x as this degree 4 cohomology class. And we put this log 1 minus q to power beta with plus over sum over all possible beta. And we minus this the last part is we sum over all possible beta 1 and beta 2, such that there's something called m beta 1 beta 2. This is log 1 minus q beta 1 plus beta 2. Okay, so as I said, so this part is the thing we want to define. This is already we know by integration of on virtual class. And this is the thing we just defined by the first formula. And what's these things? So these things in their papers, it's called meeting invariance. It's a meeting invariance which can be inductively defined by a genus 0 invariance. So I won't give you the express formula here, but I will give you some geometric explanation of what does this mean in a few slides later. So in any case, these things is determined by this genus zero invariance. So similarly, by this Mobius inversion formula, we can read off this N1 beta from this genus one chromatin invariance and also genus zero chromatin invariance. So basically, this is a definition of this N0 beta and N1 beta. So you see here is a little bit complicated, especially this last formula. So now the main conjecture of Clem and the Pandaripende is the following. So which says that this two series of numbers, they are integers. Yeah, I have to say that this is quite remarkable conjecture in the sense that you see that the chromatin invariants are purely they're random rational numbers, but through this inversion, through these two formulas, you get some rational numbers which they claim to be, they must be integers. So this is quite a non-trivial claim actually. So a few remarks about these two numbers. So the first is that the first numbers, so the first integrality is already proved by the work of Yalong and Parker using simplicity geometry method. And the second, there are many tracks by examples saying that these numbers are actually integers. So through this either torus localization or mirror symmetry, you can find out the Gopakumar-Vafa invariants in many examples. Then you just plug into this formula, then you see they are integers. So this is there are many tracks of such things. So in this talk, I will call these two series of numbers Gopakumar-Vafa. A type invariance for Calabi-Yau fourfolds. So this name comes from this a work around 1998, where this Gopakumar and Vafa they define this analog things from Gopakumar-Vafa invariance on the setting of Calabi-Yau free case. Remember in the Calabi-Yau free case is homogeneous theories. So now I want to give you a geometry understanding how to see this two series of numbers. Also, you can see the meeting numbers in the picture. So the question is how to understand these things. So the key thing is that we should consider the so-called ideal Calabi-Yau four geometry. So what it means is it means curves in such a Calabi-Yau fourfolds should deform in families of expected dimensions and have expected a generic property. So in a picture, I just draw our ideal Calabi-Yau folks like this. So the meaning of this sentence is that, first of all, we only have genus 0 and a genus 1. Remember the virtual dimension we have is 1 minus g. So in the genus 0 case, the curve should deform in one-dimensional family because 1 minus 0 is 1. Then the behavior of this rational curve should be like this. So for generic fibers, you see some a smooth rational curve. So this is some smooth P1, and they should have generic behavior, which is the generic normal bundle. In this case, it's the normal bundle should be -1, -1, 0. And as some special fibers, it can degenerate to some reducible curve with 2 irreducible components, and each component is a P1 with a similar normal bundle. Okay. So now you see that because this P1 cannot deform in this -1, -1 direction, but it can definitely deform in this trivial directions. So this curve should further, this particular component should further lives in a rational curve families. And similarly, this curve should lives in some extra rational curve families. And this family parameterized curve class beta. Let's say this is beta 2. This is beta 1 plus beta 2. Okay. And this is the behavior of genus 0 curve. So for genus 1 curve, because virtual dimension is 0, so they should be rigid. So this is genus 1 elliptic curve. Sorry, genus 1 curve, which is smooth with generic normal bundle. So in this case, it's a direct sum of free line bundles. And their tensor product is trivial to maintain Calabi-Yau condition. And they are generic members in this Picard group. Okay, so now this is we can see the Gopakumar-Vafa invariance in a very straightforward way. So for example, the N1 beta will be just the count of this isolated elliptic curve, count of genus 1 curve in curve class beta. Because they are rigid, so can we just pick up the curve class beta genus 1 curve in this picture and just count the number of such curves. This is the meaning of N1 beta in this picture. And similarly, you have N0 beta gamma, which depends on some extra 4 cycle. Remember, this is gamma is some 4 cycle. So now this 4 cycle, let me change the color. So this 4 cycle is something like this. So generically, this 4 cycle will miss the elliptic curve because this curve has complex dimension 1. The 4 cycle is complex dimension 2, but we are in a 4-4. So generically, they will miss each other. But such a 4 cycle generically will meet this rational curve family because they have complementary dimensions. So such a 2-4 cycles, they intersect a finite number of points. And then this thing is just a count, the intersection of this 4 cycle gamma with the rational curve families. in class beta. And inside is Calabi-Yau. Okay. So now in this ideal geometry, the genus 0 curve and genus 1 curve is very, very intuitive. So as I promised, I want to say what is the meeting numbers here. So the meeting numbers is then the counting of this curve family beta 1 intersect the curve family beta 2 in the expected in this virtual sense or expected situations. It's the ideal counting of the meeting of this 2-4 cycles inside Calabi-Yau. But anyway, so okay, so now it's the geometric understanding of such a Gopakumar-Vafa invariance in this ideal case. Then you can understand that the way Clem and the Pandahari-Pende they write down this complicated formula is to look at these pictures and then compute a Gopakumar-Vafa invariance using this ideal picture, and then they express Gopakumar-Vafa invariance using these two pieces of data, and then get that formulas. This is basically the idea of writing down their formula, although the computations is quite complicated and tricky. Okay, so now in the rest of this talk, so I will give another perspective for such a Gopakumar-Vafa invariance as via this Swift's vertical method. So so the thing we will use is the so-called stable pairs. Okay, so let me first introduce this notation Pn x beta. So this will denote this the moduli space of this objects in the derived category of coherent sheaf on X. So in the Euro language, this anyway, this F is just some coherent sheaf, and this OX is the structure sheaf, and we have a section of this sheaf F given by this S. And there's some requirement of this F and S, where this F is we require this to be a pure one-dimensional sheaf. And the cokernel of this section is zero-dimensional. So as in the previous case, we fix some numerical data, and the curve class of this sheaf should be beta, and the holomorphic Euler characteristics should be n. So in a picture, so what such objects can be drawn like this. So we have some Calabi-Yau for X. So we have some a curve here, and this sheaf F is support on a curve. You can understand this as some vector bundle over this curve. And there's some section of this sheaf, and the cokernel is some points sit inside this curve. Okay, so this is the geometric picture of such a stable pairs. Is some you can pretend this is some bundles over a curve. You have some section, and then you have some cokernels anyway. Okay, so such moduli space has a name. This is called the Pandahari-Pende. Thomas, just in short, to call it PT, stable pairs. So this is such things was previously used in curve counting on free folds. by this work of PNT. So the idea is that you should treat this as a similar objects as the moduli of stable pairs. Sorry, stable maps. So stable maps is give you a way to count curve via maps. But now the way we want to count curves is via the counting this sheaf support on curve with sections. So another remark is such a moduli space like this as a so-called projective scheme. We can just pretend this is a compact topological space.
There is a question in the chat.
Yes.
Maybe I read to you. Can you talk a little bit more about the code? I think it's the
Yeah,
right.
it's let's see. Yeah, I think it's how to say. Okay, so first of all, we know what is a holomorphic vector bundle, right? Anyway, we know what is a bundle. So bundle is a family of vector space over X. So there's some space over this X where the fiber is a vector space. This is called vector bundle. So a so-called this a coherent sheaf is a degenerate case of vector bundle where some fibers of this vector space can jump dimensions. So they have the fiber wise they can have different dimensions. So now this coherent sheaf category form an abelian categories, and there's a way to derive it, to make it to be a derived categories where this objects include this complex of sheaf. So yeah, I think that maybe it's better not to say this DP code. I can just say that such moduli parameterize just a sheaf F with a section. That's enough. So this sheaf F, you can understand this is they pretend this is a vector bundle over this curve. But yeah, but there's some algebraic geometric notion called coherent sheaf with this certain dimensions of support, and then you can talk about this one-dimensional sheaf, and also can talk about subsheaf, and also pure one-dimensional sheaf means any subsheaf is you don't have zero-dimensional subsheaf in this F. Yeah, maybe I think it's a little bit difficult to to say more things about this DR categories anyway. Yeah, so yeah, let's just ignore that part. Just say F is a sheaf or a bundle over a curve, and S is a section of this bundle over this curve. That's... Okay, yeah, thank you. Yeah, anyway, so if you're interested, you can look at some reference. This is you can search this DR category. DR category of coherent sheaves. Maybe yeah, you can start just by searching on the Google and just Wikipedia or anything. Yeah. Okay, the space of all such pairs forms some nice space. This is some you can consider as a compact topological space, but it can be very singular. So now we want to count, similarly as the convergent theory, we want to count the number of points in this moduli. Okay, so still we need to deal with this three issues. So the first is about this compactness issue. So in this case, this is automatic by this construction of so-called geometric invariant theories in algebra geometry. And the second is about this, I talk about this transversality first. So as before, we need to talk about this deformation obstruction theory. So in this case, we have a tangent space of the moduli space, which is this X group, which is traceless part. If you're not familiar with this X group, you can just write it as a cohomology of this X with this endomorphism of I. So in the vector bundle case, this is just like in the case one, this is a vector bundle, although it's never a vector bundle. But let's say this is a bundle, we can take this endomorphism, and you can understand as a double cohomology. Double cohomology. Yeah, I don't remember. Yeah, anyway. This is the D-bar cohomology. But for any coherent sheaf or complex coherent sheaf, this generalization of double cohomology in terms of this X group. You also have this second or cohomology space, X2, and you have X3, and you don't have other terms by dimension reason and also by stability. Anyway, this is something a little bit technical to say, but anyway. So now there's something called a set duality, where these two spaces, they are due to each other. And by set duality, the X2 just has a non-degenerate quadratic form here. So what's remarkable is we consider this holomorphic Euler characteristic. So okay, let me say that this is 0 means a traceless part. In general, this X group has a trace map to this H star of OX. Then just consider the kernel of this map. Kernel is called traceless part, denoted by this notation anyway. Then we can consider this holomorphic Euler characteristic, which is alternating sum of this dimension of this X group. I call this a small ext I. So we know that this left hand side by Riemann-Roch this is a topological constant. This is topological constant, but depending only on the Chern character of EI, and of course, taught class of X. So now the upshot using this set duality is the right hand side can be written as a twice of X1 minus minus the X2. So now the point is that X1 minus half of X2 is topological. Okay. So now the idea is like this. So remember this X2 group has this vector space with this non-degenerate quadratic form. So such things as a SONC structure And X2 with this SONC, this is a homotopy equivalence. To this group called SONR, which in this case is some half-dimensional subspace. We call it X2 plus. And this quadratic form can restrict to this subspace. There's some subspace. And now, there's some standard coordination map as in the Gopakumar-Vafa theory from X1 to X2. And having this real form, we can decompose this X2 to the plus part and the minus part, which is the square root of -1 times the plus part. And then we project to the plus part. So we use this as a neo-local coordination model. Then the idea is to glue such local model. And as before, we do perturbations to make things transversal. Then what this ends up giving you is some virtual class. So in this homology class, with this integer coefficients. Okay, so I want to say that to make this integer coefficient, you need some orientability. This orientability is about this determinant. Remember, we have the tangent space x1. We can consider determinant. This is a line now. This is a line over another line. This is determinant of x2 plus. So these two lines, you can consider this as forms you can consider quotient, and they forms a real line bundle over the moduli space. Moduli space. Because I didn't write I here anyway. So at any point here, there's this determinant. If you vary this in families, this will form in a priori non-trivial line bundle. And the orientability is to make is you need to know this line bundle is trivial. So you can make this cycle to be integer coefficients. Okay. And furthermore, I want to say that this virtual class depends on this choice of orientability. This orientation. Yeah, it's a little bit subtle here. Okay, so now having this cycle, we want to go back to this curve counting. So remember, what we do is similar as in the Gopakumar-Vafa case. We need to cook up some natural cohomology class over the moduli space. This is some in this in this particular case, we define the following so-called insertions, which is a map from the degree 4 cohomology class of X to the degree 2 cohomology class on the moduli space. So such construction is given by this Fourier-Mukai transform. So basically, you consider this moduli space cross X, you project to P, You can project to X. And over here, there's some universal one-dimensional sheaf. Such a universal object, if you restrict to a particular point here, which parameterize stable pairs. So this F will be this one-dimensional sheaf on X. So this is called universal objects. So the thing we do is that we take a cohomology class on X, we pull back to the product, and we take a cut product with the filtering character of the universal one-dimensional sheaf, then we push forward to the moduli space. Okay, so now we can count the degree. So this is degree 4. So we know Chen free is in degree 6. So total, this is a degree 10 in H10. If you push forward to P, means the integration of this Calabi-Yau fourfold integration, this fiber, then you get decreased by real A dimension because this is a complex fourfold. So 10 minus 8 is 2, so we get this degree 2. So another remark is that these things is the fundamental Poincare fundamental cycle of F, so which is integer coefficient. That's why even though we take Chen character, we get integer coefficients. Okay, now combining this insertion and the cycles, we get some invariance. So notation we use this is Pm beta gamma, which is the integration of this tau gamma to the power n over the virtual class. So now, because the moduli space exists as a space without this non-trivial automorphism, so it lives in exists as an integer. But I want to say this depends on choice of orientations. Anyway, it's a little bit subtle here, but you can ignore this part and if you first listen to this such invariance. So now the whole point of this discussion is we use a different method. This is a sheaf vertical method to cook up some counts of such sheaves upon on curve. And these are probably just by definition defined to some integers. You want such integers to be related to the whatever invariance you talked about before. So this is a conjecture of by myself and David Malik and Yukino Butoda. So it gives a correspondence between this stable pair invariance with the Gopakumar-Vafa invariance claim and the Pandari Panda define. So the formula is like this. So the left-hand side is a Gentian series of this stable pair invariance. So now, because we have a curve class parameter and the Euler characteristic parameters, we use two formal parameter Q and T to form this Gentian series. And over here, we for convenience, we put this normalizing factor, this n factorial here. So the right-hand side will be a product formula over curve classes. And with two parts. The first part is exponential of this Q T beta to some power. The power is N0 beta gamma. This is genius 0, Gopakumar-Vafa events. And the second part is this MT beta to M1 beta. So here, this MT, so this, anyway, this EXP is just exponential functions, and MT is a so-called, it's defined by this infinite product, 1 minus, 1 over 1 minus, 1 minus T to power N, and then to power N, which is called my home function. So such things is the Genting series counting the so-called Genting series counting so-called 3D Young diagram. Or equivalently this plan partitions. Okay, this is a main conjecture relating this stable pair invariance and the Gopakumar-Vafa invariance. Let me give you some remark.
Can I ask something?
Yeah, please.
Is this conjecture only for the case of Calabi-Yau fourfold or in general for
Yeah, for
Calabi-Yau and
Calabi-Yau fourfolds. Yeah, everything I talk about today is Calabi-Yau fourfolds.
okay.
Yeah, because so first of all, the right-hand side, I defined this this N0 beta, N1 beta, by Gopakumar-Vafa invariance, which only lives in degrees genus 0 and genus 1 because of Calabi-Yau four reason. So the left-hand side, they have just you can define this three vertical counting. It's because it's Calabi-Yau fourfolds. You cannot do this in, for example, Calabi-Yau tenfold. Two parts. So the first part is if you consider the dimension of Calabi-Yau to be big enough, you always only have genus 0 and genus 1. You don't have higher genus. If you consider Calabi-Yau sixfold or fivefold, if you compute the virtual dimension, you only see genus 0 and genus 1. So higher genus is a particular phenomenon for dimension less than or equal to 3. Okay. So another more technical part about this formula is in the left-hand side. So such shift counting theory is only at least at this point up to Calabi-Yau fourfolds. You cannot define such shift countings on high dimensional things, even high dimensional things at this point. So there's no way to formulate such conjecture without knowing what's the left-hand side. Yeah. Is it clear?
Yeah.
Okay. Okay, so the first remark is that the so if you expand both sides of the equations, you will see that the integrality of this Pn beta, comes from definition, implies the integrality of Gopakumar-Vafa invariance. That means if you have these formulas, so then this N0 beta and N1 beta will be automatically integers. So second things, this conjecture is written down, or you can say it's proved. In this ideal case, which I mentioned before, it's written down in this ideal geometry, and you just compute the stable pair invariance in this ideal picture. Then you can write down you can express stable pair invariance using Gopakumar-Vafa invariance and arrive at these formulas. Okay. So this is about this Gopakumar-Vafa invariance from stable pair perspective. So next, I want to say a bit about this another Swift vertical interpretation. We are this Hilbert scheme. So the notation is INX beta. So this parameterizes this maps from OX to OC, where this is surjection. where this C is a closed one-dimensional sub-scheme in X. Anyway, you can say there's a subset. And the curved class of this C is beta, and the Euler characteristic is N. So it's quite similar as before, but the stability condition is different. Previously, we didn't require this map to be surjective, and also in this case, the C does not have to be this shift does not have to be pure. So in a picture, our Calabi-Yau four-folds X, we have some curve, we can have some floating points, and such such OC is something like this bundle support on such a curve and points. And also we have sections, surjective sections. Okay, so anyway, such things has a name called a Hilbert scheme. In this particular case, is a Hilbert scheme of curves. So one similarly has a virtual class as before, which has the same degree, and we can similarly define this counts with respect to some 4 cycles, which are also integers. So there's a conjecture relation between this curve counting invariance with the stable pair invariance for myself and Marta and Ku, which say that this two numbers should be the same. Okay, so another key is that you see there's some possible floating points here, but the key is that for configuration, of points, sorry, configuration of points can be seen by from 4 cycles. So if you just consider such insertions, you don't see the curve points contributions. So to sum up, for compact Calabi-Yau four-folds, we have just the following conjecture relating. Sorry, we have conjectures relating the following several theories. So I want to say that this conjecture is the relative invariance is for primary insertions. Which means we use this 4 cycles and the first non-trivial Chen character. Anyway, this is a little bit technical, but anyway, you can ignore this part. So relating the following things. So the first is Gopakumar-Vafa theories, and also we have this Gopakumar-Vafa theories. Of course, this is defined by a claim and a Pandari-Pende. And we have the stable pair theories. We can give a name called this PT. We also have this curve counting theories. We can call it BT. So basically the previous discussion give you a correspondence between all these theories, Gopakumar-Vafa, Gopakumar-Vafa, and DT and PT. So they are related by, they contain equivalent informations, but from different perspectives. Okay, so now I still have some time. Yeah, let me just say a little bit about this how to prove these conjectures. So there are several ways to um, to try to prove this conjecture. So the first is via a word crossing in DR category. Yeah, it's a bit difficult to say because yeah, maybe yeah, maybe because the audience is not so familiar with DR category. So let me try to present in some understandable way. Okay, so let's take this omega to be an ample divisor, or if you're differential geometers, we can say this is some positive Kähler class anyway. F is a one-dimensional sheaf. So that's you can say this is a bundle support on curve. So from this two data, we can define the slope function by this Euler characteristic of F over this curve class integrate on the sorry, this Kähler class integrate on this curve class F. Anyway, this is an intersection product. So now this is lives in a rational function, rational numbers, union with some with this infinity. Possibly it could be infinity anyway, because F can be zero-dimensional sheaf. So now we introduce a definition. So we consider this pair. F is this one-dimensional sheaf, and S is a section of this sheaf. So using the previous notation is a map from OX to F. So we call this as a ZT stable, and where T is a parameter. If the following a test of slope holds. So the first is for any non-trivial subsheaf, the slope of this F prime is less than this the parameter T we fix a priori. And for any this F prime, which is a proper subsheaf, such that the image lies in F prime, then the slope of this quotient is bigger than T. Anyway, this is just definitions. So one important thing is about this remark. If you take this T goes to infinity, you will see that the this is ZT stable pairs, ZT stability is the same as the PT stability we just mentioned before. Okay, so now remember in the PT stable pair case, we use this PN exploiter as notations. So we now introduce the PNT exploit. So this is similar moduli space. This is moduli of ZT stable pairs. Such pairs as F and S, they can vary. With this numerical condition that F is a curve class beta and chi is M. Okay. So now we know that we can vary this parameter T So in particular, let me draw a picture. For fixed beta and n, we can draw this diagram. So we know that when this t is sufficiently small, then this moduli space will be empty. And in the middle, there are several so-called chambers. Where this moduli space remains the same under these chambers. That means if t belongs to this interval, this moduli will stay the same. And just if you cross this wall, then it will become something else. And in this chamber, stay the same and change, stay the same and change. And until if t is sufficiently large, then it will stabilize anyway, and become the PT stable pairs. Let's say this is a PT stable pairs, PT chambers. So as you can imagine that the left-hand side is empty things, so it's pretty well understood. Everything is zero. So through such a wall crossing, you can get more and more complicated space until we reach this PT chambers. So naive things is this is the first non-trivial chambers, and it should be easier to understand. And then just in the end, through wall cross, if you understand everything here, through wall crossing, you can get to here. Okay, so now there's a result by myself and the Ukinobutoda, which says as follows. So let X be as before, smooth projective Calabi-Yau fourfolds over C. Then for this general choice of T, so general means it's outside, if you fix a curve class and Euler characteristic n is outside a finite number of points, then this is this space is a projective scheme. Moreover, it has an open immersion to this M. This M is the moduli of objects. Yeah, it's unfortunate I have to say this again. In the Dirac category of coherent sheaf, of its fixed determinant, this trivial determinant. So basically, we take this sheaf with this section to this objects in Dirac categories. So this is open. So anyway, so what's important is the consequence of this open immersion. The consequence is that there we know such things are the means of virtual class. Okay, then we can we similarly we can define what is this n t n t beta gamma for some the gamma to be this 4 cycles as before. Then there's a more refined conjecture. Yeah, maybe I just say this in words instead of writing the formulas. So there's a conjecture formula. Sorry, the conjecture is that there's a formula relating this PNT beta with this Gopakumar-Vafa invariance. Just which generalized the previous conjecture in the PT chambers. So the remark is that when T goes to infinity, such things it recovers the previous conjectures. Okay, now as I said, it should be easier to work in directly here. But here are some mathematical results verifying these conjectures. So, which says that for the first non-trivial chambers, this conjectures holds for this local curve. Across elliptic curve E for any curve classes. And also there are many other tracks on local threefolds or local surfaces. So when I say local threefolds, I mean the canonical total space or canonical bundle of threefolds. Local surfaces means the total space of direct sum of two line bundles on surfaces. Okay. So this is the first perspective. So the second perspective is you can understand previous conjectures via so-called torus localization. Or this so-called topological vertex. So the main things is about so-called toric Calabi-Yau fourfolds. So such things are non-compact Calabi-Yau fourfolds with C star 4 action. And it contains some open part, which is this torus where this commutes anyway. So the key example we have in mind is for example X is C4, the simplest one, or you can take to be the total space of OP1 minus 1 minus 2. So this is also toric Calabi-Yau fourfolds. And also you can consider the total space of canonical bundle of P3, which is O minus 4 over P3. So to sum up, we have the following result, which is based on joint work with Martin Ku, and also later with Martin and Sergei. In the case theoretical case. So the statement is that we develop a combinatorial method to make invariants computable on toric Calabi-Yau fourfolds. And second, we use the first first method to check our conjectures, the previous conjecture, and also some case theoretical generalization. In many examples. Yeah, I also want to mention that their related work from string theory side by Nekrasov, and also Nekrasov, Pizarro. Let me check how to sorry. From this string theoretical perspective, and also the final remark is that so previously we have been talking about this mostly compact Calabi-Yau four-folds, but I want to say that the for non-compact Calabi-Yau four-folds are like this local curve. Where this total space is Calabi-Yau four-fold. We don't have Gopakumar-Vafa PT correspondence yet. So the problem is that so first of all, in this case, everything needs to be defined by torus localizations because the moduli will be non-compact. And then in this case, Gopakumar-Vafa invariants, they are rational functions. So rational functions defined by torus localization. And also potentially they can have all homogeneous all homogeneous invariants because you don't have constraint by virtual dimension anymore. So second, it is not clear what is Gopakumar-Vafa invariance because Gopakumar invariants will be rational functions, and this is maybe this is like a 1/12 plus 1/3 squared. So it's difficult to cook up a machine to get some something like integer coefficients, rational functions or something. It does not seem to make sense. So this, in a way, there's no we don't see any way to define Gopakumar-Vafa invariance in such torus localized case. So the final thing I want to say is it'll be interesting and also very challenging to work in this direction. Yeah, you may also be wondering that when I say in the previous page, we develop method to check compute child conjectures. So in what sense, right? So in these two examples, because the normal bundle of these things is negative. So in this case, if you consider this stable pairs or this ZT stable pairs, you will have a proper moduli space. So in this case, everything will still be numbers, not rational functions. So in this sense, we can make sense the conjecture and check it in examples. But for things like local curve, you must have some direction where you have a non-negative degree of this line bundle. In that direction, the curve can deform. So in that sense, the moduli, whatever moduli you consider, it cannot be proper. It cannot be compact. So torus localization is definitely necessary, and what this gives you is some rational functions instead of just some numbers. Okay, yeah, that's everything I want to say. So I just stop here. Thank you very much.